Get ready. We're going to talk about distributed systems. It's not easy stuff. I hope you're awake. I hope you had some coffee. It's amazingly subtle what can happen in distributed systems. And just to give you sort of a prediction of where we're headed, today we're going to focus on kind of the mechanics of how you make them work. And then it's going to lead into what I consider to be, to me, a really profound revelation, a fairly new result of ours, which we call the Cal theorem, which has to do with the fundamental limitations in distributed systems. And these fundamental limitations are actually particularly relevant to cyber-physical systems, okay? But they have a history in a lot of classic distributed system stuff, particularly from the database world, okay? So I'm going to use the database background in part to motivate this, but the problems get really interesting when you think of these in terms of cyber-physical systems. So let's start with the database application, okay? And I'll be very specific, and we're going to talk about Google Spanner. So Google Spanner is a globally distributed database that runs across data centers. So it actually has replicated data in data centers. In this case, they're shown scattered across the US, but it actually spans the globe. And you can do queries to this database at any one of these data centers, okay? But it is one unified database. And that creates some interesting challenges, right? Because you want to enforce some kind of consistency among the accesses to the data and updates. It also has kind of the beginnings of a cyber-physical system behavior because you need to interact with users. For example, you can think of a canonical application for this might be an airline reservation system. And you want the database to respond within, 30 to 60 milliseconds, maybe, because people get impatient otherwise. And moreover, very much like cyber-physical systems, not only is there an interaction with the environment that has real-time properties, but when you do something in the environment, it's either awkward or impossible to take it back. You can't undo it, okay? And that's really quite different from a lot of computation, which is reversible in general, okay? So let's look at this application. Now, suppose that you have, think of an airline reservation system, for example, and you want to update a record, and the query happens to come into a data center in Seattle, and it's reserving a seat on a particular plane, right? And around the same time, there's a query that comes into a data center in Dallas, asking which seats are available on a plane, on this same plane, okay? And so the question becomes, what answer do you give in Dallas, given that there's an update to the record happening at around the same time in Seattle? And as before, we can't just naively say, well, whichever one happens first would determine what the answer is, because these are geographically separated events, and so there is no well-defined order for those events, both in theory and in practice, okay? The theory tells us there's no well-defined order, but in addition, even if you forget the theory and you've only studied classical physics and you think that Newtonian time is actually correct, you still can't use it because there's no way to determine which one happened first, okay? So you can't make that the meaning. You could just throw up your hands and say, well, it's random, and just let the database respond however it responds. But you're going to get chaos in a distributed database like this, and you're going to get a lot of very problematic disagreements, like the one that we saw the last time, where two components disagree on the final state of some system. Okay, one of them thinks the aircraft engine's on fire, the other one thinks it's not. Okay, and which of those is true? Well, you don't know. Okay, so you'd like to have some form of agreement between these. So how do they handle this in the database world? Well, there's a number of techniques that have been used, but one of the most straightforward ones is that you start with the premise that you timestamp these queries. Okay, so the update in Seattle gets a timestamp T, and the query in Dallas asking for which seats are available gets a timestamp R. And now you define the semantics of the database to be dependent on the numerical order of those two timestamps. Okay, notice that's not the same thing as asking which one happened first, because these are just two numbers. Now, obviously, in order for this to be useful, you probably want these numbers to be drawn from clocks that are reasonably well synchronized. Okay? But once you've got these numbers, you have a well-defined meaning for what's going to happen, what the right thing to have happen is. Okay? And you'll see that, the correct answer to the Dallas query is clear. It just depends on the order of these two numbers. But the problem we have, of course, is that one of those numbers is in Seattle and the other one's in Dallas. And how do you compare two numbers that are, more than 1,000 kilometers apart? So one way you could do it, of course, is just wait for the data to propagate. So in Dallas, you don't respond until you get some timestamped update. And now, under certain assumptions, you can issue a correct response, right? The assumptions would be that all of the updates that are coming get to you reliably and that they come in order, okay? And so if you just sit there in Dallas and wait until you get an update, and then you compare the two numbers and issue a response, you could give a correct response, but that's not going to satisfy your real-time requirements, right? Because maybe nobody is reserving a seat at the moment, so you're not going to get an update message. Okay. So what could you do? Well, one possibility, which is a classic technique called the Chandi Misra technique, which dates back to 1979, is just that you constantly send messages. You're sending messages along every path, timestamped messages. You're sending them in timestamp order. And if your real-time requirements are that you need to respond within 30 milliseconds, then you better send messages at least every 30 milliseconds, okay? And the vast majority of these messages are saying, I don't have anything to say. Just repeat it. Timestamp is this, I don't have anything to say. Timestamp is this, I don't have anything to say, okay? Now, this is a pretty common solution, particularly in a control systems context, in industrial automation and in avionics and in automotive electronics, where you treat the whole system as a sampled data system, and everything is essentially sending messages to everything else every 30 milliseconds. And most of those messages are carrying no useful information, okay? So Chandi Misra is just a slight generalization of that doesn't require the samples to be regularly spaced. And it doesn't require them to be, in a control systems context, you tend to think of them as samples of some sensor data, as opposed to, events that have occurred or not occurred, okay? So Chandi Misra is a little more general in that the messages don't have to be uniformly spaced, and they can carry event information rather than samples of some underlying continuous waveform. Does that make sense? Okay. So Chandi Misra works, but it's pretty expensive. It uses a lot of bandwidth, and there's sort of a lot going on with no information. So there's another approach that dates back to 1985 due to Jefferson, who called it time warp. And the idea there is that when you get a query in Dallas with some timestamp R, you just go ahead and reply. And if you later get a query that happens to have an earlier timestamp, you take it back. Okay? So it's backtracking. But the obvious problem here is that if you have side effects in the physical world, then you can't take those back. Okay. By the way, I mean, this kind of backtracking does occasionally occur in distributed database systems. You've probably experienced it yourself. You know, you get through the whole process of making a reservation for something, you get to the final page, you know, click on the pay button, and you get an error message, and you have to start all over again. And there's a schema in databases called a transaction schema, where the state of the database gets tentatively updated. Okay. But then the updates only get committed when there's a consensus that's formed across the whole database. It's called a transaction schema. And occasionally those transactions fail. And part of the art in designing those systems is to make the failure of transactions relatively rare. Okay. In the context of cyber-physical systems, it may not be enough to just make them relatively rare, because if the side effects are directly doing things like, you know, controlling the surfaces of a flying airplane, the side effects in the physical world could be seriously problematic if they're based on incorrect data. Okay. So, yeah, so you can't backtrack the side effects. There's also this backtracking technique has a very big cost, which is that you have to have consistent snapshots of the state of the system that you can roll back to. And those are not trivial to construct. They can be relatively easy in a very narrowly defined space, but in general systems, they're really quite difficult to construct. Okay, so a third possible approach is to rely on a coordinator, which one example of which is a standard that's out there called the high-level architecture, HLA. It's a standard that's been around since the mid-90s, roughly, okay? And it involves having a runtime infrastructure, which is kind of a broker that mediates the flow of information. So the way that this works is that when you get a query, so by the way, you know, the way you can implement this in lingua franca. It's actually incredibly easy to implement if you use the TypeScript target, because creating a web server is a one-liner, okay? And so you create a web server, and it just runs in the background, and whenever a query comes in, an HTTP request comes in, you get a timestamp event, right? So when you have that timestamped event, then this local part of your system queries the runtime infrastructure, right? Specifically what it does in the HLA is it sends it a message called the next event request, and it sends the timestamp, right? It's a notification to the runtime infrastructure that I've got an event with timestamp R, I would like to process it. Can I process it? It's asking the RTI a question. Is it safe to process? Okay, safe to process is going to be a keyword here. Well, how do we know whether it's safe to process? Well, when this web server over here gets a query and it creates a timestamped event, it issues a next event request also to the runtime infrastructure. Okay, and at this point now, it's very useful for the runtime infrastructure to know about the connection topology, to know that this guy is upstream of this guy, and it can then just compare these two numbers, okay, and it can allow the downstream guy to proceed with R if R is less than T. So if R is less than T, it will issue a time advance grant of, well, in general, what it'll issue is some time advance grant that is less than or equal to the minimum of these two. If this is all that's going on in the system, it'll be equal to the minimum, okay? And it sends that time advance track to both of them. They're both able to advance their notion of logical time to match that number, and they can then proceed to process the event if R is less than T. Okay. Now, of course, there's a number of issues with this. One of them, of course, is that if there's no events happening here, you're not getting any next event requests. So how do you proceed? Okay. And I'm going to show you how this works in lingua franca. Lingua franca has an implementation of this style of solution. And it does not require this to just produce a bunch of null events, except in one circumstance, which I will show you, the circumstance in which that arises. Okay, but it can often be a lot more efficient than the Chandi and Misra technique, which is requiring continuous notification that nothing is happening. Okay. Then there's a fourth technique. So I've given you three so far, right? Chandi and Misra, Jefferson's time warp, the high-level architecture, which has the centralized broker. And now the fourth technique, which has gotten reinvented a couple of times. It really has its roots in work by Leslie Lamport way back in the early 1980s, but it was never implemented then. I believe that my group was the first to actually refine it, make it implementable, and implement it around 2007. And we called it TIDES. And then it was reinvented independently by Google, and it's used in Google Spanner. And it is the technique that underlies Google Spanner. So let me explain to you this, this technique. And here's where I hope you've had some coffee. I hope you're ready. Okay. One of the reasons that these things are hard to understand is that there's multiple timelines involved. Okay. And that always makes things confusing because natural language doesn't deal well with multiple timelines. Right. Okay. So I'll give you what the punchline is, right? First, so you'll see where it's going. So the punchline is going to be that if you get a query, it gets assigned timestamp R, then all that this guy has to do is watch its local clock. Okay? And when the local physical clock exceeds a threshold that depends on that timestamp, the event is safe to process and it processes. No communication necessary with any broker, no communication with anything else in the system, just watch your local clock. Okay? The question is, what is this threshold? This is just a number, all right? It's the numerical timestamp of the query plus 3 numbers, okay? One of which is an assumed execution time bound on this thing. Second one is an assumed network latency bound on the communication. Okay, this. And the third one, what do you think the third one is? Clock synchronization error. And an assumed bound on the clock synchronization error. You have to take a guess. How far off could these clocks be? Okay. One of the interesting things about this, by the way, is that question makes no physical sense. Okay. I'm gonna tell you a little bit about clock synchronization. It's a really fascinating problem, but it turns out that the sum of these quantities is actually an observable physical quantity. The individual numbers are not. They fundamentally cannot be measured. Okay, but the sum can. So that's what makes this a realizable system. So let's go through this pretty carefully. First, we assume we've got a local clock, physical clock on each platform, right? We assume that the timestamps are drawn from that local physical clock. We assume a bound on the time that it takes between when the timestamp is assigned and the message is launched into the network. Okay, so that we call that bound double. We assume that there is a bound on the network latency. We assume then that the event will become known to this subsystem. An event with timestamp t becomes known to this subsystem by this time. The value of the timestamp plus the execution time bound plus the network latency, right? But this time is by this guy's clock, right? Not by this guy's clock, which is why we have to add to this bound on the clock synchronization. Okay, so the event with timestamp t is known on this platform by the time its local clock gets to this threshold. Right? So why does that lead to the conclusion that this becomes safe to process at this time? It would have arrived. If this guy were to receive the message with a timestamp earlier than R, it would have arrived by this time, according to its local clock. Okay? So think about it. All you're doing is you get a message and say, okay, it's got a certain timestamp. You watch, say, okay. If there was going to be a message with an earlier timestamp, it would have gotten here by now, and it didn't, so I can process this. Very simple, right? Yes?
The sum of WLE, you just have to measure your system for a while and then set it as that sum, or how do you actually, I assume that it's not always the exact same value.
It's not always the exact same value, and how you come up with these assumptions is pretty tricky. But let me explain to you how you make the measurements, okay? So all you have to do is that as soon as any message becomes known to you, compare its timestamp against your local clock. And that is an estimate of this sum.
Yeah.
It's actually not even an estimate, it is the sum, right? So you could collect a bunch of those. As you keep getting messages, you could keep learning what is the network actually doing to you, and you could, so we call this difference between the timestamp of the incoming message and the local clock the apparent latency. Okay, it seems to be the amount of time that it takes a remote message to get to you, but it's not really, because you don't share a common timeline with the source of the remote message, right? So we call it the apparent latency, and it's an observable quantity, right? You collect some data on it, make some measurements of your network, and then add a little slop. You can come up with a conservative bound here, and then start running your system in this way where you're just watching local clocks. But you can actually do even better. You can turn this analysis around the other way. So for example, suppose that your database application has a requirement that it must respond to a query within 30 milliseconds. Well, what does that mean? That implies that you better have a network where the sum of these quantities doesn't exceed 30 milliseconds, the vast majority of the time, right? So that imposes a requirement. So in the case of Google Spanner, they do synchronize clocks across data centers, and they have a roughly 30 millisecond requirement for this kind of database. So they can put a bound on the communication latency, right? They actually, for Google Spanner, they will actually get a dedicated fiber trunk connecting to data centers. And so the latency is not too far off from the speed of light constraints. between data centers. It's a bit more than that just because the circuitry on both ends is considerably slower than speed of light phenomena. That tends to have a significant effect on the latencies, but the latencies can be determined by just, the propagation time for the most part through that trunk. And then that tells them how precisely they have to do clock synchronization, which tells them what clock synchronization technology should they use. Okay, if you have really tight latencies, you might need to use an atomic clock at each of the data centers. They don't need to do that for Google Spanner because 30 milliseconds is plenty of time. Right? So we get this principle that's based on this assumption. Okay, these assumptions on apparent latency. So what are the advantages of this compared to the previous ones? Well, unlike the HLA-based approach, there's no single broker that becomes a single point of failure, right? This is a very decentralized control system. Each component just has to watch its local clock to determine what to do. It can operate independent of any, even if communication fails completely, it can keep operating and keep advancing its time. It can process events with no network traffic at all, which is quite different from the Chandi and Misra approach, where you have to send a lot of null messages. Okay. If your network is reasonably static, you can compute these bounds statically. Okay. That might be applicable, for example, in an industrial automation setting, where you might have a network based on TSN, the time-sensitive networking technology built on top of Ethernet, or you might have a more dedicated proprietary network like Profinet that has nice real-time properties, and you can characterize the latencies quite effectively over those kinds of networks. So in that sort of setting, you can probably come up with some pretty tight bounds on these numbers and be able to operate your system with quite a lot of confidence with those numerical assumptions. Okay, so yeah.
I think I understand these points, but I don't really get the view of the system still. So, what do we actually gain from implementing this? Because you said even if communication stops completely, the system can still work. But then this sum doesn't really have any meaning left, right? Because this apparent latency is just the infinite.
Yeah, so that's a very good question. But so one of the key things to observe here is that there's an assumption here, right, about these numbers. And is it possible for that assumption to be violated in the field? Of course. Any assumption you make about any system you design could be violated in the field. Okay? But there's a big difference here. We've made the assumption explicit. Moreover, you can detect when violations occur, if they matter, right? Sometimes the violations could occur and they won't matter. When will they matter? Suppose that I make an assumption about network latency and it's violated. What am I likely to see?
Some changes on the platform image,
But what changes?
Something that the platform A already happened.
Well, it's even simpler than that, right? So when I say that an event is safe to process, okay, what that means is that I'm making a decision that my notion of logical time can advance to R. There's no events earlier than R there. That's the assumption I'm making, okay? If my bounds are violated and I later receive a message that has an earlier timestamp, then I know that my bounds were violated, okay? It's very easy to detect. You detect it right at the input of these messages. As soon as the message comes in, bam, you know that your assumptions were violated. You can no longer execute your program as defined, you now have to have a fault handler, right, in order to handle that situation. What Spanner does is, in fact, a transaction schema on top of this. That's exactly what they do. Okay, so they go ahead and they process the event R within the 30 milliseconds. All right, they update a local copy of the database, but they don't make it persistent yet. All right? What they do instead is whenever there's an update to the database, in kind of the background, they form a classic distributed consensus about the update, and then they commit the database transaction. Okay, and that works okay for airline reservation systems because, you know, if you reserve a seat, you know, as step 7 of a 25-step process, and you get to the end and the transaction didn't commit, you get the error message and you start over. And all you want to do is design the system so that the number of times that this assumption gets violated is small, right? In cyber-physical systems, you're going to want to be more conservative, probably, particularly if these events have safety-critical side effects. Okay. So, you know, here's a way that you could, you know, apply this in practice to the kind of systems that we were looking at. You've got a couple of sensors that are, and some computation that's happening on the sensor data, and we split this across 3 different computational platforms, so that the fusion and actuation is happening on one platform, the sensing and computation is happening on other platforms, and there's network communication between these. All right, and you get a time-stamped event. You deem this to be safe to process when this set of conditions is satisfied, and you just have to, you know, kind of do the fault analysis, right? You know, you make your assumptions clear. You assess how likely your assumptions are to be violated. Any assumption you make could be violated, right? You decide based on the safety criticality of the system how likely these violations are. What mitigations can you do in the way of fault handling? Things like that. Okay. Does that make sense? So just as background, you know, this the core of this technique can be found in this 1984 paper by Leslie Lamport. Although it doesn't really have the same form as in Lamport. And the interesting thing about, I mean, as in Spanner or Tides, but the interesting thing about Lamport's paper is that he actually was using this technique specifically to get fault-tolerant distributed systems. So he was actually using it more for detecting the failures in the network than for getting correct behavior in the absence of failures, right? So that's why, to some degree, it was really a bit of a transformation when Tides and Spanner came along, because they were kind of using the same idea, but for a completely different purpose, right? Which was to actually coordinate the execution and get deterministic results from the execution, as long as your assumptions were satisfied. But Lamport was using it as a detection scheme for faults. So then we published this paper in 2007 and built an operating system that we called TidyOS. It was inspired by this TinyOS system. It was kind of, it worked in a similar way. It was a library that you link against, okay? But it was a library that implemented this technique on bare iron microcontrollers. And then Spanner came along and applied this to a much bigger scale system than we ever thought was possible. You know, we were thinking small industrial automation kind of things with local networks and so on. They showed it global. Okay, so let's look at how this plays out in lingua franca. And this is the thing that the last assignment, the next one that you're going to do, that I want you to experiment with. And there's some rough edges with this because it's pretty raw technology at this point. But I think it's working well enough on Linux and Mac machines and in C and in Python. So you can hopefully use either of those, although it was developed first in C and only in a mad scramble in the last few days to bring Python up to speed. So hopefully it'll work out. But anyway, what you do is for any given program in lingua franca, if you want to make it distributed, you just replace the main keyword with federated, okay? And let me drop out of PowerPoint here and just do this in real life. Federated.lf is this file right here. Here is its diagram as reported. And the key difference is simply the federated keyword instead of main. If I make it main, the little cloud disappears. If I make it, federated, the little cloud appears. And then you can do, there's a number of parameters, right? So we actually have two different coordination mechanisms available. By default, you get a centralized coordination mechanism, which is very conservative. It's the one that's based on HLA, okay? And the way that you switch between these is with a target parameter. So you say the default is that coordination is centralized, okay? But you can also make it decentralized, in which case you get the tides and spanner technique. All right, but let's stick with centralized first. And you don't, if you're going to use centralized, you don't need to say anything here. You can just use, let the default take over. When I code generate this, it's actually going to produce 3 distinct programs. Well, actually, no, it only produces 2 programs, one for each federate in this case. So it's doing the code generation. It's going to produce 2 programs, okay, plus a shell script that launches the 2 programs on my local machine. All right, so let's actually have a little bit of a look at that. So I had removed the bin and the source directory, but now they're back. All right, there's something in the bin directory. What is it? Well, let's have a look at it. It's a script. Okay. It's a script that launches the RTI and then launches the federates, all on the local machine in this particular case. Right? So these will be separate programs. And then it also generated those programs. So if I look in the source gen folder, I've got two subdirectories, C and P. The reason for that, for those names, is that my federates are called C and P. Okay, so there are 2 directories. Let's just look in C for the count. What's in there? Well, a bunch of stuff, but most relevantly, where is the actual Python program? Right here, federated c.py. That's the program that the script will run. All right, and this is just a bunch of other supporting files. Okay, now this is meant to be a distributed system, and by default it just puts everything on the local host, the same machine that you do the code generation on, but you can change that. For example, I could put the RTI on a machine at Berkeley. Oops, I think it's actually, the name of the machine is this. And as long as I have SSH access to this, it will actually launch an RTI on that machine and then the two federates will by default run on this machine, but they will coordinate through the machine in Berkeley. All right. I could similarly put any of the federates somewhere else. Okay. This actually will not work very well. Why do you think this configuration would not work well? There's three programs, right? There's the RTI, the runtime infrastructure, and the two federates that need to communicate. The RTI does the coordination. The problem here is that this will, by default, put the RTI on my machine here. But the federates won't have access to my machine here. My machine here has been assigned an IP address using DHCP. That IP address isn't known to the federates, so the federates won't be able to communicate with it initially. So when you make this system distributed, you need to put the RTI at a well-defined IP address, and then the RTI will handle all of the other machines discovering each other. Okay, the RTI needs to be a machine you can find. There's a very nice scheme here where you can also have the federates generated in Docker containers and then deploy them on, any of a variety of cloud service providers. So you can get a virtual machine somewhere, get an IP address for that virtual machine, put your RTI on that virtual machine, get all your federates into Docker containers and deploy those into the cloud, and maybe some of them into edge nodes and some of them into the cloud. Okay, so those are the kinds of things that we're trying to pursue. Okay, and the basic building blocks are all there for that. But on this local machine, if I just generate the code locally and run the script, let me do it in a, well, no, I guess I can, no, I think I better do it in a terminal that's a little bit bigger. Okay, so now I can manually compile this federated.lf. The problem is that it creates these Python modules and then it has to be able to find them. Okay. Okay, so it has started two federates. It gives me the starting times for the two federates. And then both federates are printing, well, I guess no, only one of them is printing to standard out. So it's telling me what it received and at what time. Okay, so I promised some rough edges. This is the first one. We don't actually have a packaged release of the RTI. You have to build it from source. Okay. These are the instructions. Hopefully that'll all work for you. Okay, but you won't be able to run any federated programs until you do that. We will eventually fix that, but it's not fixed yet. Okay, so then we've got this very simple federated program. Instead of just running it using the script, because that kind of hides a little bit what's going on, I'd like to show you what happens if you just run the three individual programs by hand. All right, so the first one that you have to run is the RTI. And the RTI, when you start it up, takes at least one option, which is you have to tell it how many federates to expect. So that's the -n. So this tells it expect two federates to join. Then you can optionally specify an ID for your federation. So this means you can have multiple RTIs running on the same machine and not have the federates all join the wrong federation. Okay, so you can think of that as a federation ID. So when you start it up, it gives you some acknowledgements, and then it says it's just listening for federates. So then you start up one of the federated programs. like this count guy, all right, by just invoking its runtime command. This is for the C version. In Python, you would say Python 3 and then pass it the Python generated code. Okay, but that's the only difference. For the C version, you directly invoke the executable, and then you can optionally specify a Fed ID. Most of us don't bother with the Fed ID while we're just testing systems because you just run one federation at a time. Okay, so then it acknowledges that this is going to be federate 0. It's connected to the RTI at localhost at some port, and start execution tells me how many worker threads it's using. Then you start the other federate, okay? And at that point, once the other federate has joined the federation, the RTI will actually issue a message saying, oh, I've got all the federates now. And then there's some handshaking that happens for the federates to agree on a starting timestamp. Okay? And then they start executing. So, yeah, so that's, you know, when you're debugging these programs, for example, it's actually pretty useful to just run them individually, because one of the things that happens when you run them with the script is that all of your outputs get jumbled because they get sent to the same screen. So it's hard to tell which output is coming from which program, which can make debugging rather difficult. Okay, so let's go through a little bit of the details of how this works. So when the federates first start up, they just open a socket connection to the RTI. So this is, in order to do that, they need to know an IP address for the RTI and a port number. There's a default port number, okay? So, and the default IP address is localhost. If you're familiar with networking software, localhost is a default name for the machine that you're currently running on, but it's a particularly constrained name. So if you're running something on localhost and it opens up a socket server on localhost, that socket server is not visible to any machine on the network. Okay, it's only visible on the local machine. So it's pretty secure. You're not, you know, opening up your machine to the world when you start up an RTI on localhost, because it can only be connected to by processes that are on the same machine. You can alternatively open, you can start the RTI at an IP address 0.0.0.0, which is also the local machine. But the operating system interprets that differently and does open it up to machines on the network. Okay, so any machine that knows your IP address will be able to connect to that RPI. Yeah, does that make sense? Okay, so so the federate opens a socket and then gets sends its federate ID, which was code generated. Okay, the RTI will acquire some information. Well, I'll show you how it does it. Okay, but it first, you know, either acknowledges or rejects, because if the federation ID doesn't match, it'll just reject and say, "Go away! I'm not your RTI. Go find your RTI somewhere else." Okay, so other federates do the same. Once they're all connected, okay, then each federate tells the RTI about the topology of the system. So in particular, this guy is going to send a message to the RTI that is a data structure that says that I'm directly upstream of this other federate. Okay, so the RTI builds a picture of the interconnection between the federates during this startup phase. It turns out to be pretty useful for it to have that. The second thing that the RTI does is synchronize the clocks. Now, if you're running on the same machine, there's no need to synchronize the clocks because they're using the same physical clock. And in fact, the clock synchronization phase gets optimized away. So the runtime detects that they're on the same machine and does not synchronize the clocks. But I'll explain to you in a minute how the clock synchronization works, but let me come back to that because I want to tell you how we discovered that you absolutely must have a clock synchronization phase here, right? Because the next thing that the federates do is they tell the RTI what their current physical time is according to their local clock. The RTI then chooses the maximum of all of these, maximum of these numbers, adds a buffer, which I think defaults to like a second, and sends a starting time back to all the federates, right? So then the federates will start executing with this as their first logical time. Now, remember that by default, in lingua franca programs, logical time chases physical time, right? So the program is not allowed to get ahead of logical time. All right. What will happen if these two machines are on different time zones? We actually saw this happen before we had this clock synchronization phase. Okay, we started up a federation with one of the federates in Germany, one of them in California. They were 9 hours apart. The RTI picked the maximum of two physical times, which were 9 hours apart. Okay, and then sent the start time to these guys. And one of the federates had to wait 9 hours before it could process its first event, right? Because logical time chases physical time. So it couldn't advance its logical time to that start time until 9 hours had elapsed. It's a pretty slow start for a program, right? Yeah.
Is that the only problem that synchronization fixes?
It's not the only problem, no. The problem, the synchronization also becomes very important whenever you have physical actions in the system, which assign timestamps to events using the local clock. Yeah. So you need this clock synchronization layer intervening anyway whenever you have physical actions.
But it can't be a perfect synchronization.
It can never be a perfect synchronization. In fact, let me explain to you how it works because I can explain clock synchronization in one slide. Okay, that's all it takes. One slide. Okay. I should have updated this slide, however, because master slave they're bolted. You don't call them that anymore. You have a main clock and a secondary clock. Okay. So what do they do? Well, the main clock is going to send a message to the secondary clock, but it timestamps it with its local physical clock. So T1 is the time according to its local clock at which it's going to send the message. It then sends the message, and that message is received at a time T2, okay, plus whatever the discrepancy is between these two clocks. Okay. Then at T3 plus the discrepancy. So the discrepancy is actually what we want to know, but we don't know it yet. So we just assume that these two clocks are not synchronized. They disagree on the current time of day by E, but we're treating this guy's clock as the truth. Okay, so this is the time at which this is received according to this guy's clock. Right? This guy sends a response back, and the main clock timestamps the response with T4. Okay, and then it sends T4 back to the secondary clock. So now, what does the secondary clock have? Well, it has four numbers: T1, T4, T2 plus E. Okay, well, no. It has, yeah. It has T2 plus E, right? Or does it have T2? Right, because, well, it has T1 because the main clock sent it T1. That was the payload of the message.
Yeah.
Okay, but the issue is, I said that this was the time at which this was received according to this clock, which this guy doesn't know. Right?
The time of T1 minus E or something.
Right. That's, well, it's not the time of T1. It's the time at which it receives the message. Okay. So all it can know is the time at which it receives the message according to its own clock. Okay. Yeah. So that's it. So this sum is the time at which it receives the message according to its own clock. And T2 is the time at which it receives the message according to this guy's clock. Okay. And we don't know what the difference is, but we know what the sum of these two numbers is because we know what time we receive the message according to our own clock. Similarly, we know the time at which we send the reply according to our own clock. Okay. So the four numbers that we have are these two sums and T1 and T4, which were both sent to us. Okay. So the round trip delay for a message to go from here to here and back to here is simply T4 minus T1 minus the difference between these two. Right? You can see it geometrically here. Right? The amount of round trip delay is simply the difference between those two differences. Everybody see that? Now we make a key assumption. We assume that the round trip delay is symmetric. Delay in each direction is the same. Never perfectly true, right? But if it is close, we get a very good estimate of the one-way delay by just dividing R by 2, right? That's going to be the one-way delay. So you can then figure out that your estimate of the clock error is, so if the delay here, the actual delay for this message is in fact R over 2, right? If it is, if we have perfect symmetry, the actual delay for this message will be R over 2. Our estimate for the delay is the difference between this number and this number. The estimate doesn't agree, but it's in fact exactly by E that it doesn't agree. Okay? So in the event that this difference is exactly R over 2, then then this will be exactly E. All right? Does that make sense? Okay, so once we have an estimate for the clock synchronization error, all we have to do is shift this clock by E. Right, so this is what Lima Franca does during startup. It just calculates a clock offset. And then that clock offset gets added every time you ask for the local time of day. You get the local time of day plus that clock offset. By default, it does this clock synchronization only once during startup. And then it assumes that the operating system is already running a clock synchronization algorithm to keep the clocks relatively in sync. And most operating systems do that. Okay, they're running a protocol called NTP, which uses exactly the same algorithm to synchronize the clock of the machine to some master clock, in this case in Cupertino. Okay. But you can also, by setting a target option in Lingua Franca, choose to have the clock synchronization continue during execution of the program. And so then it just repeats these estimates and dynamically keeps adjusting the clock offset while your program is running. Okay. So this is, these are two IEEE standards that use exactly the same protocol. This one is for wired communication over Ethernet. This one is for wireless communication. It's used in Wi-Fi systems. Yeah.
To do this for each potential secondary conflict.
Yes, you need each.
Or
Right. Each secondary clock has to synchronize to a single main clock. And by default in lingua franca, the main clock is the clock of whatever machine is running the RTI. Okay. All right. So, okay. So now let's talk about the difference between centralized coordination and decentralized. So they both, in lingua franca, they both have an RTI, and the RTI does this startup procedure the same way for both. Clock synchronization happens whether you're using centralized or decentralized. The joining of the federation is handled in the same way, and so forth. But once startup is finished, at that point, the two techniques diverge. So for this particular example, the first thing that's going to happen after the startup phase is that this guy is going to tell the RTI that its next event on its event queue has timestamp 0. Doesn't say timestamp 0, but this is relative to the start time. Okay, these timestamps are hard to read if you don't make them relative to the start time. But there's an event at the start time because of this clock timer. Okay, so it just tells the RTI that its next event is at 0. And there's now both the federate and the RTI know that there's no need for a response because this guy doesn't have anything upstream of it. So there's no reason for it to not just go ahead and advance its time to 0 and go ahead and process the event. It doesn't have an upstream federate, right? So this is where the topology of the interconnection matters. For the downstream guy, for this particular example, we had a timeout of 5 seconds. So the program wants to end at 5 seconds. And consequently, the next event on this guy's event queue has timestamp 5 seconds. So it notifies the RTI of that fact. Right? So it says, my next event is 5 seconds. And it's asking the RTI, is it okay for me to advance my time to 5 seconds? That's the question. Right? So what does the RTI say? Well, it doesn't say anything yet. It just doesn't respond. Okay? Because it cannot provide an assurance to this guy that it won't get an event with an earlier timestamp. Okay? In fact, if the RTI is paying attention, it kind of suspects it will get an event with an earlier timestamp because this guy has already told it that it wants to advance its time to time 0. Okay, but it doesn't know for sure whether there's going to be an event at time 0. So it just doesn't respond. So this guy is able to advance to 0 and invoke a reaction, and then it sends a message. And in centralized coordination, all of the messages flow through the RTI. All right, this is part of what makes it such a conservative technique, but it's also, you can immediately see now, okay, well, that makes me nervous. There's a single point of failure. There's a bottleneck because all the communications are going through the RTI. But nevertheless, that's the way the centralized coordination works. That's why it's called centralized coordination. So at this point, the RTI forwards the message, which has timestamp 0. And it also then knows that there can't be any more messages with timestamps earlier than that because there's no other incoming connections. It knows that topology. And consequently, it goes ahead and gives this guy a time advance grant, but not to the requested 5 seconds. But it asks to advance its time to 5 seconds, but it says, no, you can't do that, but you can advance to 0. And that enables this federate to invoke this reaction and handle that event with timestamp 0. Okay, so this guy, so what happens next? This is a typo, sorry. This should advance the tag to 0, 0, not 1, 0. Okay. So the next thing that happens is that this guy will notify the RTI that its next event of interest is at 1 second, because this is a periodic timer, right? Again, no need for a response. This guy once again notifies the RTI that its next event is at 5 seconds. That's the timeout time. And then they just keep going, iterating through this process until they have reached their timeout time, at which point both of the federates resign and they're done. Okay. These slides are a little bit out of order. I apologize for that. So let's look at what happens specifically at logical time 1 second. Okay, so this says handle the timer event at 0. Oh, no, this is a different system. Sorry, this has feedback. Ah, right. That's why this is. Okay, so we're done with this example. This example is extremely simple. It's got only 2 federates, but moreover, there's only a feed-forward communication. Things get a lot more interesting when there's feedback. Okay, so in particular, this is a program that is kind of on the edge of having a causality. If I were to just reverse the order of these 2 reactions, I would have a causality, or reverse the order of those 2. Okay, so this is barely avoiding a causality loop. There's no logical delays in the feedback loop, and we want to be able to handle this. All right, so let's look particularly at what happens when both of these reactors have already completed the logical time 0 processing. So this guy tells the RTI that it's finished with time 0. This is a logical time complete message, LTC, logical time complete. This guy tells the RTI that it has finished, say, the 500 millisecond. Okay, so we're kind of in the middle of the execution. This is handled the timer event at 500 milliseconds. This is handled the timer event at 0. So the next thing this wants to do is at 1 second. The next thing this wants to do is also at 1 second. Okay. So what do? Well, they both tell the RTI that. They say that their next event of interest is at 1 second. What do you think the RTI should do at this point? Can it tell either of them to advance to 1 second? The only thing it knows is who's upstream of whom. It doesn't know the internal structure. It knows there's no causality loop, but it doesn't know where the causality loop is broken. Okay, so think of it from this perspective. Can it promise to either of these 2 that they have seen all the inputs with timestamp 1 or less? It can't. Right?
If there is no causality loop, then it can just say, take 1 can advance, the other can.
It could, but which one? If it tells this guy it can advance, right, then this guy will go ahead and process this event, finish with logical time 1, and later receive an input message with logical time 1. And because of the order of these 2 reactions, it should have invoked this reaction before this one, but it failed to do that. right? So it can't tell this guy to advance. It could tell this guy to advance, but it can't tell it to complete the processing at time 1, because it still could get an event at time 1 here. Okay. So the original tides technique and spanner both don't actually solve this problem. Okay, what they do is they say, all right, if you have a network like this, you've got to have a logical time delay somewhere in the network. So you have to have an after delay here or here. Okay, but lingua franca actually solves this problem. So how does it do it? Well, it sends back a message to both of these federates, which we call a provisional time advance grant. And what the provisional time advance grant says is go ahead and process any events at 1 second that you can process that have no dependence on network inputs. Okay, it's a provisional time advancement. So what happens here is this guy knows that it has an event at time 1. But because this is reaction 2, which has to occur after reaction 1, there's a dependence on a network input. So it cannot process it cannot invoke this reaction 2. Instead, it has to block, waiting for something to happen, because it has a dependence on a network input. But this guy does not. It's got this event at time 1, and the local runtime can tell that this reaction has no dependence on this network input. Okay, this reaction occurs lexically earlier than this one, so it's okay to execute this at time 1. We can go ahead and execute it and send this message. And then it'll go and block here because it doesn't yet know whether it can invoke this reaction or whether it will need to invoke this reaction. Okay, so what happens in response to these provisional time advance grants is that there's an execution of that reaction followed by a blocking on the input here. And specifically, it blocks until either it gets a time advance grant, an unprovisional one, or it receives a message. Okay? And in this case, this guy will receive a message. This will unblock. This reaction will invoke. That will then unblock the execution of this reaction, which will then produce the message here. That message will unblock this guy, which will then enable this reaction to invoke. And then you're done with the cycle. Okay? Yeah.
Are those very many time steps that they happen at individual time steps, or do they all happen at 1 second?
They all happen at 1 second. So the interesting thing about this is that all of these events are logically simultaneous. Okay, but they have a causality relationship between them. And that causality relationship is enforced by this handshake with the RTI.
The super dense time concept, what was the second half that you took over?
Yeah, so the super dense time concept doesn't even enter into play here because if the microstep were incremented, that would be treated as a whole new timestamp. Okay, so in this case, this is all occurring at 1, 0. Microstep 0. Yeah, that's right. It's a logical time. So with these feedback systems, the actual control of the execution can get kind of intricate, as you can see, right? But the nice thing about this is that a lingua franca program that runs unfederated will run exactly the same way federated, no matter how far apart you put the federates. You get the same behavior, right, through the coordination of the RTI. That of course comes at a cost, right? You can imagine that you could easily build systems that would really run quite slowly. Okay. And we're going to look at this. This is going to be the essence of the Cal theorem. All right. I'm going to show you how to prove that you cannot have strong consistency, which is an agreement on everything that happens at every logical time, without it having a cost in availability. Okay, cost in the latency in your ability to respond to messages. So Cal in Cal theorem stands for consistency, availability, and latency. All right. Okay, so let's talk a bit about decentralized coordination. So decentralized coordination is way more efficient, okay? But it makes stronger assumptions about the network, and it fails in different ways, right? Centralized coordination could fail if the RTI, or the machine that the RTI is running on dies, for example. Whereas decentralized coordination can keep running even if the RTI dies. In fact, it can keep running if any federate dies. So after the startup phase, the communication between federates is direct through a socket. Okay. So for this particular example, this extremely simple program, I can almost get away with just making it decentralized and not doing anything more, but it doesn't quite work. All right. If I take this program and just make it decentralized and try to run it, then some of the messages get through, but I get error messages, and I get them at really pretty understandable points. The first one occurs at the very start time, where the very first message gets received at microstep 1 instead of microstep 0. So it was actually sent at microstep 0 and received at microstep 1, which is not the correct semantics in lingua franca, right? Why do you think that happened? So what's happening here? What is constraining the federates' advancement of logical time? So remember that in the decentralized coordination is using the same technique that Spanner uses and that Tides uses, where if a federate has an event to process, it only has to watch its local clock before it can decide when it's safe to process. And remember that the safe to process offset was the sum of these three numbers, the execution time bound, the network latency, and the clock synchronization error. And by default, lingua franca assumes the sum of those three numbers is 0. That's the default. What else would it pick? What else would be a reasonable default? So it turns out then that when at time 0, this guy looks at its local clock and says, oh, okay, I'm already at time 0 plus 0. It's safe to process. I go ahead and process the event. Okay. But this guy does the same thing. Right? It looks at its clock and says, oh, I'm at time 0. I can process the 0 time events, no problem. I don't happen to have any, so then I'll just complete time 0 without processing any events. And now I receive a message that wants to be at 0, 0. The next event that's going to be of interest here is the one at 5 seconds. And the only thing that keeps it from advancing to 5 seconds is that logical time chases physical time. So it doesn't want to advance to 5 seconds until the physical clock has advanced to 5 seconds. Okay? But when the physical clock advances to 5 seconds, I then get another error. Because I go ahead and complete my execution as soon as my physical clock hits 5 seconds, and then I receive a message later that has the timestamp 5, and I say, too late, sorry, I finished execution. Okay, so the problem here is that the offset, the safe to process offset defaults to 0. There's two ways to correct this, but it gets, let me first show you that the problem gets even worse when the destination actually has stuff to do, right? So it's trying to advance its clock periodically, then you start to see errors quite frequently, all right? So when you go to decentralized coordination, you have a little more work to do. You've got to actually design your program. You have to figure out what these safe to process offsets need to be, or alternatively, you can introduce after delays, okay? So here, if I just simply say, all right, well, the message between these two is going to have a logical delay of 10 milliseconds. Okay. Then all the errors disappear. This thing works fine. As long as the total sum of those numbers, the execution time plus network latency plus clock synchronization error, as long as those are less than 10 milliseconds, this program will execute exactly as if it were unfederated. Okay. So that's one technique. We call this the poor man's tides technique. The very simplest way to get spanner-like behavior is just introduce this logical delay and make sure that the logical delay is big enough to compensate for your actual delay. Right? But there's an alternative technique, which is to set a non-zero safe to process offset. So you do that as shown up there. You just create a parameter called STP underscore offset that has type time and set its value to 10 milliseconds. And remember, logical time chases physical time. What this says is logical time chases physical time plus 10 milliseconds. Okay, so in other words, don't get any closer to physical time than 10 milliseconds behind. That's what it says. That's the safe to process offset. And then you get exactly the same logic as if you had executed unfederated, right? So now there's no, notice in the previous execution, these timestamps are actually incremented by 10 milliseconds. So it's not the same behavior as the program without the after delays. Okay. What is the difference between these from an engineering perspective? Why would you pick one or over the other? You can get this to execute correctly either by manipulating the timestamps using after delays, or you can get it to execute correctly by introducing a safe to process offset. What's the difference? Yeah.
You don't have to wait.
Well, in both cases, you have to wait, but there's a bit of a difference, right? There's a very essential difference between these. If you think about when you can process this timer event. If I've got a timer event here, 1 second, for example, when can I process that? After 1 second, physical time. As soon as my clock hits 1 second, I can process it. What about here?
Here it's kind of gone.
Yeah, but these are relations between logical and physical time. This is why this is so hard, right? We've got multiple timelines. So remember, logical time chases physical, right? In this system, as soon as my physical clock hits 1 second, I can process this. In here, I can't process it when my physical clock hits 1 second because of this safe to process offset. I have to wait an additional 10 milliseconds beyond that 1 second before I can process this. Okay. So the issue here is that, in a sense, my ability to respond to a timed event has been compromised by this safe to process offset. Okay, got a timed event. Imagine, this timer is driving an actuator. Okay, I'm trying to make something happen in the physical world, and I'm having to delay it by 10 milliseconds. That's a loss of availability of 10 milliseconds. Think about it, if this event were a physical action coming from a sensor. Sensor raises an interrupt request. It gets timestamped. If I have a safe to process offset of 10 milliseconds, I have to wait 10 milliseconds before I can process that. There's a 10 millisecond latency in my response to an actuator event. Right? No such delay here. Safe to process offset is 0. And I can go ahead and process this event immediately. Okay, so I have better availability, but I have more inconsistency because I've introduced a 10 millisecond logical difference. So from a logical perspective, the event that gets communicated here, this federate has a different view of it than this one, and they differ by 10 milliseconds. Think about it if these were database record updates, okay? This guy thinks that the record update occurred at some particular time. This guy thinks it occurred 10 milliseconds later. There's a 10 millisecond inconsistency in their view of that database. This is a fundamental trade-off. You cannot avoid making this trade-off when you have network latencies. You have to choose between losing availability or losing consistency. Okay, that's going to be the topic on Monday. Okay, I'm going to prove to you that that's the case. You cannot avoid that. Yeah, so one way to convince yourself that this really is a loss of availability is it's very straightforward. Put a deadline at this reaction. Okay, you put a deadline of 10 milliseconds, it's going to get violated every time. Okay. The event occurs at 1 second. It can't be processed until 1 second plus 10 milliseconds because of this guy. So as soon as you decide to process it, you've already violated the deadline. And consequently, every invocation results in a deadline violation. So whenever you insist on strong consistency, you end up compromising availability, which compromises your ability to meet deadlines. Okay, so here's the teaser. This is the theorem that we're going to see on Monday. It's completely accidental that it happens to coincide with the logo for my institution. Right? But it says consistency and or availability must be sacrificed as network latency increases in any distributed system. And one of the nice things about lingua franca, which I think is unique to lingua franca, is you can choose whether and how much consistency and availability to sacrifice. Right? Maybe 10 milliseconds is okay. If this deadline can be 20 milliseconds instead of 10, then you're probably okay with this design. You can have strong consistency and still meet all your deadlines. But if you need this deadline to be 10 milliseconds, then you cannot have strong consistency if you need the safe to process offset to be 10 milliseconds. I've never seen the ability to do this trade-off so explicitly in any other system. It's just not there. Okay. So the other thing is, remember that when you have a safe to process offset, well, you always have a safe to process offset if you're using decentralized coordination. The way that you write a fault handler is similar to a deadline fault handler. Okay, so you write your reaction to this input. As long as there's no violation, meaning you're not seeing things out of timestamp order, then the body of the reaction gets executed. As soon as you see an event that's out of timestamp order, you execute this instead. So now you can put your fault handler in here. So notice this is a very explicit requirement on network behavior. And this is a very explicit handler for when that requirement gets violated. It's nice. It's a nice thing to be able to have both of those things. Make your assumptions explicit. Build in a handler for when those assumptions are violated. Okay, especially with networks, because networks can always break. So interesting. My computer, it tells me my battery is low because I'm not plugged in. So centralized coordination is really much more straightforward, right? In that it doesn't need any assumptions on network latency. Okay, it's going to give you the same behavior as an unfederated program. It may be slow. If the RTI dies, it'll fail altogether. In fact, if any federate dies, it'll fail altogether. Okay, so it's pretty brittle. But as long as things are working correctly, you get this perfectly deterministic behavior. The federated execution with decentralized coordination is really more, it has more requirements, but these requirements are made explicit. Okay. Make your timing requirements explicit with deadlines. You make your networking assumptions explicit with the safe to process offsets. The clock synchronization error and the network latency are actually bundled together. You cannot separate those two. There's no, it's impossible to tell the difference between clock synchronization error and network latency. Okay. So on this clock synchronization thing, I just want to, so here's two clocks on the Berkeley campus that are not synchronized. Okay. Sort of inexcusable, but there you have it. All right. Clock synchronization is pretty widely available, but the level of precision with which it can be implemented is highly variable. There's this very nice IEEE standard 1588. It's called a Precision Time Protocol, PTP. Okay, and it's the core part of a whole suite of standards that are part of what's called time-sensitive networking, or TSN, which is a standardization effort that is still underway because I keep elaborating the standards, but it's basically it's the 802.1 group of the IEEE, which is the group that's responsible for Ethernet. Okay, so wired networks. And TSN is an Ethernet-based networking standard for time-sensitive applications. Lingua franca can work without that, okay? But if you put it on a TSN network and turn off its own internal clock synchronization, you get really very, very good clock synchronization, right? On a local area network, 1588 will give you agreements on clocks that are sub-microsecond, you know, down to tens of nanoseconds of agreement. This has actually been used in industrial automation, but more in cutting-edge designs. It's not, you know, ubiquitous by any means. But this is an example. I think I showed this example on day one. This is a printing press from Bosch Rexroth. And these are Ethernet cables. And they started shipping this this printing press in 2008, and it's probably one of the first really major serious industrial automation applications to use Ethernet and TCP/IP, which are internet standards. Okay, but it does so with this underlying very strong clock synchronization protocol, and it eliminates effectively much of the variability in network latency by using the clock synchronization. So in an Ethernet network, the biggest cause for latency jitter is dropped packets. Okay, and packets get dropped whenever buffers and switches overflow. You can completely prevent buffer overflow by just regulating the timing of everyone's use of the network. But to regulate the timing of the use of the network, you need synchronized clocks. And the network gives you synchronized clocks here, and you can just orchestrate the use of the network so that you never drop packets. And consequently, you can get very reliable latencies just out of Ethernet and TCP/IP. And that's an existence proof. So clock synchronization is getting better, right? GPS receivers have become pretty cheap, and you can synchronize clocks globally to under 100 nanoseconds using GPS. So if you have the luxury of having a GPS receiver, it's pretty easy to get very tight clock synchronization. This IEEE 1588 standard, this is my favorite application of it, very aggressive application. This is the Large Hadron Collider, which is a 27-kilometer ring that spans Switzerland and France. So it's about 10 kilometers in diameter. They have machines all around this ring with synchronized clocks. And they use exactly the protocol that I just described to you to synchronize those clocks to tens of picoseconds of accuracy. Okay, that means that if you could simultaneously observe two of these clocks 10 kilometers apart, they would disagree on the current time of day to under 10 picoseconds. Okay, 10 picoseconds is about this far at the speed of light. Yeah. The jitter, you can actually engineer this to make the jitter as small as possible, as small as you like, but at the expense of a longer acquisition time. Okay, if you're willing to put up with getting your clocks in sync relatively slowly, you can make the jitter very, very small. Okay. Yeah, so the project that did the clock synchronization on this is called White Rabbit. And they use certain tricks. Remember that I told you that for the clock synchronization protocol to work, you have to assume that the latency is, the one-way latency is half of the round-trip latency. So they actually build the wiring to try to make sure that that's the case. So if these two computers are communicating, they will run a single fiber. They don't actually run it through the middle, they run it around the ring, right? It's a single fiber, and both directions of communication occur on the same fiber, so that the temperature effects on speed of light are the same in both directions. Okay? Because all you need is symmetry. Right? If your latencies are symmetric, you can, in principle, get perfect clock synchronization. Right? They have to be perfectly symmetric. Okay? So it's a beautiful project, but most people don't need picosecond accuracy. These guys do because they have particles flying around this thing at close to the speed of light. So they need very, very tightly synchronized clocks. But okay, so I'll stop there, and on Monday we will talk about Cal theorem, where I will show you that these trade-offs between consistency and availability are absolutely fundamentally unavoidable.